we're going to look at a special class of reactions called redox reactions, or oxidation reduction reactions. This consists of two separate reactions that have to occur simultaneously. So a reduction reaction will involve a reduction in the oxidation number. We'll assign oxidation numbers in a moment. In the process, it will gain electrons. So it's consuming electrons. Oxidation involves an increase in oxidation numbers. And to do that, it will lose electrons. So these redox reactions are the reactions that we use for our batteries. In our batteries, these two reactions are physically separate. So the oxidation will produce electrons. We drive those electrons through our device to power the device. Then the reduction reaction consumes the electrons. Redox reactions are also, unfortunately, cause a lot of damage to us. They cause rusting and corrosion of bridges, underground storage tanks and pipelines. But when we are trying to identify whether we have a redox reaction going on or not, we do that first by assigning oxidation states, and then to see if we have a change in our oxidation states. And so we have rules in this. So this will be posted on the Canvas page, so we can download it and get a good look at it. So the oxidation state of a element, a neutral element, is 0, regardless of what subscript might be on the element. The oxidation state of a monoatomic ion is the same as its charge. The summation of oxidation states for a neutral compound will add up to 0, and the summation of oxidation states for a polyatomic ion will add up to its ionic charge. So we generally will use those summation rules for each compound. We assign the easy oxidation states first, and then use the summation rule for the last or hardest oxidation state. Now, a couple of rules here we already know. The alkali metals, group 1 metals, have an ionic charge. The oxidation state will be +1. The alkaline earth metals, group 2 metals, have an oxidation state of 2, an ionic charge of 2. Fluorine in a compound is going to be assigned -1 all the time, no exceptions. Hydrogen in a compound with nonmetals is going to be a +1. When there's a metal in that compound, then the hydrogen turns into a -1. Oxygen in compounds is usually a -2, except for peroxide. And the only peroxide, H2O2, hydrogen peroxide, that's the only one I expect you to recognize. If I give another peroxide, I'll identify it in the name of the compound. Oxygen can also become a -1/2 in superoxide. We will not have superoxides in this compound, in this course. But it shows that when we're not dealing with a monatomic ion, we can end up with a fractional charge as an oxidation number. The halogens are normally -1, except when halogens are combined with fluorine or oxygen. Then we use the summation rule to figure out what the halogen is. The oxygen also, when combined with fluorine, we use the summation rule about what oxygen is when combined with fluorine. So fluorine is the highest one that gets the -1 value. The group 6A nonmetals below oxygen will have a value of -2. and the group 5A nonmetals, starting with nitrogen, will have a value of -3. So let's use these rules to assign some oxidative states. So we assign the easy ones first, oxygen is a -2. So we use summation rule to figure out what that nitrogen is. So nitrogen plus 3 oxygens will add up to the charge, -1. Nitrogen plus 3 times a -2 will add up to that -1. This, of course, is a -6. We bring it to the other side. We have a +6 minus 1, so we end up with a +5 for our nitrogen. Sulfur hexafluoride, the fluorine gets a -1. We have sulfur plus 6 fluorine will add up to 0. And this is 6 times -1. We move to the other side and it becomes a +6. Potassium permanganate is an ionic compound. We could just break it apart as a K plus and a MnO4 minus, so give us the same answer. So potassium is going to be a +1, oxygen's a -2. Then we use a summation rule to figure out what the manganese is. So we got potassium plus manganese plus 4 oxygens added up to 0. So we have a +1 plus our manganese plus a 4 times a -2 equals 0. So that's a -8. We bring our numbers to the other side. Manganese, we bring that -8 becomes a +8. The +1 becomes a -1. And we end up with a +7 for the manganese. The Fe3O4 is a magnetite, a form of iron that forms that magnetic mineral. So we assign a -2 to oxygen and use summation rule for the iron. So we have 3 irons plus 4 oxygens will add up to a 0. 3 irons plus 4 times a -2 will add up to 0. 3 irons equals a +8. We move that -8 to the side, becomes +8. And it looks like we can go to Fe is 8/3. However, this is an ionic compound. So we expect iron to be a monatomic ion. So not a fractional number like that. So we don't like that 8/3. So we're not going to use that. But we have 3 irons add up to 8. So we have Fe plus Fe plus Fe equals our 8. And if we look up what iron is, we see that iron commonly does either a +2 or a +3. So we do 3 plus 3 plus 3 plus 3. That will add up to 9. We change it into a +2, a +3, a +3, and that gives us our 8. So we're going to have 2 different types of monatomic ions going on. So we're going to have a 1 plus 2 and 2 plus 3s. And this is an example. I'm not going to have something this style on our quizzes or tests. So for reactions, we're going to have 3 types of questions associated with it. The first one being, is a reaction a redox reaction or not? And then if it is a redox reaction, we have what's being oxidized, what's being reduced, and another set of questions I will define in a moment. So what we want to do is to answer whether it's redox or not is to say whether we're changing any oxidation numbers. So we go through and do the easy ones. Alkali metals, sodium's a +1, oxygen's a -2. We'll use summation rule for the chlorine. Sodium's a +1, oxygen a -2. We'll use summation rule for the chlorine. Sodium's a +1. Chlorine, there's no oxygen present, so chlorine is a -1 here. So for the sodium hypochlorite, we add up the 3 elements to get 0. We have a +1, a -2, plus our chlorine will add up to 0. So the chlorine, we switch it across, we have a +2 -1. So chlorine is a +1. So let's do that for the sodium chlorate. We have our sodium plus chlorine plus 3 oxygens add up to 0. We have our +1 plus the chlorine plus 3 times a -2 add up to 0. That's a -6. So chlorine, we move that -6 across, we get a +6. We go +1 across, we get a -1. And the chlorine comes out to be a +5. So we do see that we have some changes going on. The oxygen and sodium is always the same, but chlorine changes. It's doing a +1 to a +5. It's also doing +1 to a -1. So we have a redox reaction. Let's look at the next one. We assign the easy charges, the -2 for oxygen. We have a monatomic ion, so the charge is, the oxidation number is the charge. Monatomic ion, the oxidation number is the charge. Monatomic ion, the charge is the oxidation number. A neutral element is 0. Over here, we want to assign a +1 for hydrogen, -2 for oxygen. Summation rule says they add up to 0, so that's good. So let's just figure out what the manganese is in permanganate. So we have Mn plus 4 oxygens add up to the charge of -1. Mn plus 4 times a -2 equals our -1. That's, of course, the -8. Move to the opposite side, 8 minus 1 gives us a +7. So oxygen is not changing, the manganese is changing from 7 to 2, and the chlorine is changing from -1 to a 0. So we have a redox reaction. The next type of question that we'll ask is, what's being oxidized, what's being reduced? So here the manganese is going from a 7 to a 2. We're reducing that number, so that's reduction. And when we're talking about what's being oxidized and reduced, we can talk about the element and not necessarily the whole compound. Either one, if you give them a whole compound, they'll generally be happy. So in this case, our manganese is being reduced. Chlorine is going from -1 to a 0. That's the increase in oxidation number, so that's oxidation. And of course, that's the element chlorine being oxidized. Up here, the chlorine is going from +1 to a +5. That's an increase of oxidation number, so it's oxidation. It's also going from +1 down to a -1. That is reduction. So in this case, the chlorine is being both oxidized and reduced in the same reaction. This has a special name, a disproportionation reaction. So we have one more type of question that we can ask about these reactions. The agents, oxidizing agents and reducing agents. So the agents are always going to be a reactant. And for the agents, we like to specify the whole compound, not just the element that's participating, but the whole compound, or polyatomic ion. So the oxidizing agent causes something else to be oxidized. In doing so, it gets reduced, or an element in it gets reduced. A reducing agent causes something else to be reduced. In the process, it gets oxidized, or element in it gets oxidized. So for a disproportionation reaction, this is where the oxidation agent equals our reducing agent. So they're both the sodium hypochlorite. For the bottom reaction, you see that the permanganate is being reduced. The manganese and permanganate is being reduced. That means it's causing the oxidation of chlorine. So our oxidation agent is the permanganate. The reducing agent is going to be getting oxidized, and it's the chloride that's getting oxidized. So our reducing agent is the chloride. Is this visible? Yeah. So some common reduce. Let's see, start with the other page here. Where's the other page? Yeah. So some common redox reactions. Basically anything that involves an element. In general, if we have an element in a reaction as a reactant or product, it'll be a redox reaction because the element is zero, and generally they will not be zero in compounds. I've only found one exception to that, which I will not use on a quiz or test. So combination reactions involving elements, decomposition reactions involving elements, combustion reactions. Combustion reactions, by definitions, are rapid oxidation reactions that will produce heat and light. So of course the oxygen starts off as a zero oxidation number, and it ends up with a -2 charge normally. And then here's another example of a disproportionation reaction. Hydrogen peroxide decomposes into water and oxygen gas. H2O2, the oxygen has a -1 charge, and water is a -2, and as the element, it's a 0. So the oxygen is being both oxidized and reduced at the same time. And single displacement reactions, they also involve an element. So in the first one's hydrogen displacement, a active metal like the alkali metals will react with water itself, and they knock hydrogen off the water, releasing hydrogen gas as the metal dissolves and turns into a hydroxide. Acids will dissolve most metals. In the process, again, we exchange the metal with the hydrogen, and we produce hydrogen gas in the process. The metal displacements, one metal will exchange with a metal in the compound. And these will only go one direction based on the activity series. And then halogen displacement has a similar type of series on that, where one of the halogens can replace another halogen in a compound. And just to finish up here, some common oxidizing reducing agents. So oxygen itself, in air, it's about 20% oxygen. Of course, once we start a fire, oxygen feeds the fire. Ozone, O3, is a good oxidizing agent, stronger than oxygen. We use ozone in some drinking water treatment systems to destroy organic compounds and bacteria. Hydrogen peroxide, we use that as a disinfectant for cuts and wounds. It'll oxidize bacteria and kill them. Nitric acid, good oxidizing agent. Perchloric acid has been used as rocket fuel. Chloric acid, chlorous acid, hypochlorous acid are all good oxidizing agents. The salt of this is bleach, so it'll help oxidize dirt to get rid of the color of stains. Potassium permanganate, the halogens are all good oxidizing agents. Some common reducing agents, hydrogen, the alkali metals, lithium aluminum hydride is common as a laboratory reducing agent. Sodium boron hydride, B2H6. Carbon has been traditionally used to reduce iron ore down to elemental iron. Sulfite, ferrous iron, iron 2 iron, oxalic acid. These are all common reducing agents.